Nuclear chem. Now that we've talked about isotopes and we know what isotopes are, we're going to apply that knowledge to this new topic of nuclear chemistry. Maybe familiar with nuclear chemistry from nuclear power plants. Just so happens within those nuclear power plants, nuclear chemistry is happening. And that nuclear chemistry is allowing for cities, towns, regions of states to be powered with electricity. So pretty cool stuff. We're going to talk about nuclear chemistry in this video. Radioactivity. Radioactivity is the whole idea behind nuclear chemistry and the idea that things are constantly decaying. They're not necessarily decaying like, banana wood in the garbage disposal, but they're decaying in a way where they're in an excited or energetic state, and they're trying to become less energetic. And in chemistry, the less energetic state is called the stable state. So they're trying to become stable. They're starting unstable, like this radioactive atom that we have right here, and they're releasing either energy in the form of light or heat, or they're releasing a physical particle. So we're going to look at examples of both of these types of or decays where both of these things happen, and we're going to be able to understand why and where the stability comes from. So there are three types of nuclear decay. We're going to break each of them down, look at examples, and hopefully feel comfortable by the end of this video. First one is alpha decay. Easy to remember, alpha, the letter A, the first thing that we're going to be talking about. In alpha decay, we are starting with a radioactive nucleus, like we have in this diagram right here. And that radioactive nucleus, to become stable, is going to get rid of or release an alpha particle. An alpha particle basically is a helium nucleus. So it's got a mass of 4, an atomic number of 2, and we write He. That's how we would write an alpha particle generally. That's how we're going to write it in class. So we'll just keep that in mind. So when we release an alpha particle, we're releasing a helium nucleus. So that means we're getting rid of a value of mass of 4, and we're getting rid of 2. Our atomic number is going to decrease by 2. I know that the atomic number comes from the protons, and the mass number comes from protons and neutrons. So that makes sense as to why when we look at an example up here, we have our new isotope, or our new species in radon, with the mass of 222 and an atomic number of 86. Now, something I want you guys to notice over here on this example, notice that our atomic number is 88 and our mass number is 226 to start. And then we get rid of this helium nucleus or alpha particle. And if you add 4 to 222, that's 226. If you add 2 to 86, that's 88. Law of conservation of matter. Matter can neither be created nor destroyed. So that's where that applies right here. So in alpha decay, we're getting rid of a helium nucleus. Let's see some examples. So in this first example, we're starting with polonium with a mass of 210 and an atomic number of 84. Now, it's going to be very important for you to make sure that you have a periodic table handy when you're working on these, because it's just a lot easier to do that. So we know in alpha decay, we know that we are going to be getting rid of a helium nucleus. Once you get rid of a helium nucleus, we know that our mass is going to decrease by 4. So 210 minus 4 is 206. And then 84 minus 2 is 82. Now, you just look at your periodic table, you find the element with the atomic number of 82, and then you write that symbol down. So, once you get your periodic table out and you find element number 82, you will find that element number 82 is lead, Pb. Man, it took me a while to find. So here's our alpha decay of polonium. We produce an alpha particle, and we now have lead as our more stable isotope. All right, let's look at example number 2. In example number 2, we see that we're given our new isotope in uranium, but we need to see where we started from that. Where did we get that uranium from? Well, we know this is alpha decay, so we know we're going to get rid of an alpha particle, so that's going to be one of the things on the right side. Now we need to do the reverse of what we did in that first example. We subtracted a helium nucleus from our start to get our new lead, but now we need to see where we started. So we're just going to do the reverse process and do some adding now. So 94 on the bottom, 242 on the top. Now let's find 94 on the periodic table. Should be somewhere towards the bottom. That is plutonium, Pu. So hopefully you're catching on now. It's simple math, really, if you really think about it that way. So let's work on these next two a little bit quicker. If you want to, you can pause the video, try them on your own, and then I'll go over the solutions when you are done with that. All right, so we've got thorium. We know we're going to get rid of a helium nucleus. I always like to do the helium nucleus first if I can, just because it helps me do the subtraction straight across. So 90 minus 2, 88. 238 minus 4, 234. Let's find 88 on the periodic table. It's going to be radium, Ra. So the idea here is that the heavier elements, the heavier isotopes, are going to be less stable than the lighter isotopes, or the isotopes with less mass. So you can see that all of these new species that we've produced are lighter than what they started from. All right, last one. This is 88. This is 226. So if I go to 88 on the periodic table, I feel like we've already done this one. We have. It is Ra. All right, so that's alpha decay. Very cool. Now continuing on, we're going to look at beta decay. This is the second type that we're going to look at. In beta decay, we're now releasing a beta particle. What's really happening inside the nucleus, we are releasing or replacing a neutron for a proton. So a neutron's getting shot out, a proton is now taking its place, and we're also going to be releasing an electron in the process. We're getting rid of a negative charge. Now what's interesting, because we're replacing a neutron for a proton, the mass number is just going to stay the same. Remember, mass number is protons plus neutrons, so if you just replace one for the other, it's basically just a wash. It's still 0. So our mass number is going to stay the same here. Now the atomic number is going to increase by 1. Why is that? Well, that's because we brought this proton in, and we know that the proton ties directly with the atomic number. So whatever happens, if we add a proton, our atomic number is going to increase. So we've got our example up here, rubidium 87. We're going to get rid of this beta particle, which is essentially an electron. Electrons have negative charges. We also bring in a proton, so our atomic number increases. So that's why it's at 38 now, and that changes our element to strontium. So that's beta decay for you. Main thing you want to remember is that the mass number stays the same, and the atomic number increases by 1. Let's go ahead and look at some examples now. All right, so this first example, we have our products, or the right side of the equation. Now we want to do what we started with. Let's just write our beta particle. Remember that we always want to make sure that we are doing our math correctly and that we know where we're starting with or where we're ending with. So with beta decay, we know that we gain a proton in the process, and our mass number stays the same. So my top number is going to be 14 here. And we gained a proton. So let's just do, you can also do this math. Look, 6 minus 1 is 5. So we gained a proton. And our element is boron, B. All right, so remembering that our mass number stays the same and that we gain a proton in beta decay, if you can just work around that and work maybe backwards if you need to, be good to go. All right, so we have nitrogen 13. I'm just going to write my beta particle first because that helps me with my math. And then we know that our mass is going to stay the same, so that's 13. And we gain a proton, so we're going to have 8 protons now. 8 protons changes my element to oxygen. All right, same thing. Just pause the video if you want, or if you still need a little bit of help, I'll walk you through the next 2. Looks like our plus sign ended up all the way over here. Let's just get rid of that. All right, so this is still beta decay. Let's draw our beta particle. We know that our mass stays the same. We gained a proton, so we need to have one less on this side. Search for number 37 on your periodic table. Where is it? Rb, rubidium. Boom. Beta decay. Last one here, we got potassium. Let's write that beta particle. That's supposed to be a 0. Sorry. All right. And mass stays the same, 40. Gain a proton, 20. And element number 20 is calcium. Boom. There you go. Beta decay. Second type of decay. Now, we're going to get into the third one. It's not going to take us a lot of time because I find it to be the easiest one. Gamma radiation. High energy photon emitted by a radioisotope called a gamma ray. You may hear gamma rays in like comic books and stuff. That's fiction in comic books, but gamma rays are real. They just won't turn you into the Incredible Hulk. They'll just do some other damage and some things that you don't want to get. The difference with gamma radiation, however, is that we're not releasing a particle, we're releasing a wave. So waves are, or light especially, is a photon does not carry mass. So the mass isn't going to change, and we're also not losing a proton or gaining a proton, so the atomic number is not going to change either. So real interesting, but if I just had an example, let's just say that I have uranium. Powers nuclear power plants, and it underwent gamma radiation, which is written like this: 0, 0, gamma. This is the gamma sign right here. If you see, the top number is 0, so that's not going to change my mass. That's going to make that 238. The bottom number is 92. That's not going to change it, so it's still uranium. We didn't end with anything different. All we did was we got rid of this energy in the form of gamma radiation. Gamma radiation is high energy, is a high energy wave. You would see it on the electromagnetic spectrum with the UV light, with microwaves, things like that. So gamma radiation will find that it's the easiest. You don't change anything. You just need to know that you're releasing a gamma ray. It's a wave rather than a particle. If we're talking about the relative penetrating powers or how strong the decay or the radiation is from alpha, beta, and gamma, alpha is our weakest. And as we talked about with gamma, gamma is pretty strong. So alpha will be stopped by a piece of paper. Nothing to worry about with alpha. Alpha particles, it's not going to cause any damage to your DNA or cause any cancers or anything like that. Now beta, on the other hand, a little bit stronger. It can get through paper, but it's not going to get through your skin. So again, not going to really do too much damage to you. Not going to be really, shouldn't be worried about it too much as long as you're not exposed to it for too long. Now gamma, however, gamma is very harmful. See, as you can see, that can get through this paper, can get through your skin, which means it can do some damage, and then even worse, can get through steel and get through lead. Or it can get through lead depending on how thick it is. It needs to be about 3 feet thick of lead for it to be stopped. So that's the relative strength in which the nuclear decays go. I hope that these examples that we went through in this video helped. I'll be sure to include a video where it's strictly only practicing examples where they're all mixed up. There are 2 other types of decay, but we're not going to cover that in this video. Hope you enjoy. Leave in the comments if you have any questions. I'll see you in the next video. Until then, keep working hard on your chemistry.